Okay, so finally we are done with the governing equations, and now we're going to look at boundary conditions. So why do we even bother with boundary conditions? I'll try to give you physical reasoning and mathematical reasoning. Of course, physical reasoning is kind of obvious because the inside of a domain, inside, what happens inside? If I want to know, calculate temperature inside the domain, it is of course affected by what goes on at the boundary. And so then to solve the governing equation inside to get temperature, we have to somehow relate to the conditions at the boundary. Mathematical reasoning goes this way. So suppose we are doing a slab, okay, for which we um, have the equation for conduction only. The equation goes like this: rho Cp del is k del square T del x square. Okay, if it is for transient, then we keep this, but for a steady state we drop this term. So for a steady state situation in a slab, steady, we get the equation d square t dx square equal to 0. If we solve, we get t equal to dt dx equal to c1, t equal to c1x plus c2. Um, but what are these c1s and c1 and c2? So those are the constant of integration. They need to be found. So without that, you know that it's a straight line, but you don't even know its slope or its intercept. In other words, you cannot have a number that you need in real world. You only have the trend. So to get the number, we really need C1 and C2. Okay, how many types of boundary conditions are there? Well, we're going to study 3 types, and that takes care of most of the practical situations. So the first one, type 1 boundary condition. Um, let's take a physical situation. So let's say condensing steam burns the hand surface, and I am interested in knowing the temperature in the tissue. So in doing the bioheat transfer, I need a boundary condition at the surface. So condensing steam, from physical considerations, it is known that it can maintain the surface temperature basically equal to the steam temperature. So boundary condition then in this case is the surface temperature is given. Because of this condition of condensing steam, the surface temperature is going to be given as a value, and in this case constant. And then another example, physical situation is in the winter, air is really blowing over your surface. Okay, um, I mean really blowing. It's not just mildly breeze, but really blowing. Then we can consider the skin surface is to be at air temperature. So Ts equal to 0. Notice what we are getting at is in this case as well, the surface temperature is known. So surface temperature known is the type 1 boundary condition, or surface temperature given to us. In this physical situation, uh, this is not true if wind isn't really blowing. We're going to learn more about these later. So this is true only when only for blowing. Another example of type 1 boundary condition. A cryoprobe is at liquid nitrogen temperature and it is used in a cryosurgery. And so at the surface of the probe that touches the tissue, again you have this kind of a boiling situation that this liquid nitrogen is going to be boiling there and maintaining the surface temperature of the probe to be minus 196. So again you see the form that surface temperature is known or given. So then we generalize all this and we write that if this is where we want to do heat transfer, this is our domain and this is our boundary. Okay, so at the boundary then we write T at x equal to 0 is some Ts. So this Ts is known. It's a known value. We write it symbolically, but it is 10, 50, 100. For example, steam condensing, it will be T at x equal to 0 is 100. Okay, then we come to type 2 boundary condition. A physical situation could be solar radiation. So type 2 boundary condition means the solar radiation is constantly coming to the surface. It doesn't matter how hot the surface gets. So here the heat flux is given. So on the surface the heat flux is given. So let's say if it is 500 watts per meter square. 500 watts per meter square would always be coming. So what is given at the boundary is a flux Qs double prime is equal to 500. Another situation, in a laser surgery, if you have the laser on, then it's going to constantly give the heat. It doesn't matter how hot it gets or how much destruction happens, the laser would constantly give heat. So the condition at the surface would be some heat flux is equal to a value, whatever value corresponds to the laser. Now, of course, the flux can change with time. As you turn on the laser, it will be 2000. When you turn off, it's going to be 0. So it can change with time, but it is the flux that is given, not the temperature. We don't know the temperature. The temperature will keep changing depending on how long you have the laser on, but it's the flux that is given. So now we just write the type 2 boundary condition for the general situation. So you can think of it this way. So suppose there is a heat flux coming in, okay, then on the surface it gets absorbed and that raises the temperature. So it raises the temperature this way. So at this point the heat can get conducted in. So all we can say is the heat flux Q S double prime is related to the heat conducted in, which is this part. So minus K del T del X is the flux or conductive flux, and that's equal to whatever is falling on the surface. An example would be infrared heat lamp shining on your back at 4000 watts per meter square. That would be written as minus K del T del X at x equal to 0. So this is your x equal to 0 is your back surface, and minus K del T del X is the flux. So the conductive flux, the conductive flux going in is equal to what's falling in here. So 4,000 falling in and it's going into there. The temperature is not something I know. So if you leave it longer, it's going to get hotter, right? So we don't know the surface temperature. Now, two special cases of the type 2 boundary condition are very useful. One is a highly insulated surface. So like we were saying that there is a heat flux here. Well, if you really insulate it well, then we can have zero heat flux, zero. And so then my condition is at this boundary heat flux is zero if it is well insulated. So we write this as del T del x equal to 0 because it's minus k del T del x equal to 0, which means the same. The other condition that you will get quite often is suppose the whole process of heating is symmetric. So we have a nice symmetric slab that's being cooled, let's say, from the surface. Then at the symmetry line, there's always going to be the temperature profile is going to be symmetric. So if temperature profile is going to be symmetric, then if you take a point on this side and take a point on the other side, so T at let's say minus delta x is equal to T at plus delta x. Okay, that's the meaning of symmetry. And so then T at delta x minus T at minus delta x over delta x is equal to 0, which means del T del x is equal to 0. A simple way to see is the profile is symmetric, then it increases and then it starts to decrease. So of course at this point the slope is going to be 0. So this symmetry is one special case and insulated is the other special case. Then we come to the last one, type 3 boundary condition. So this time the physical situation can be air flowing gently over your face, gently, not really blowing. So then the skin surface is not going to be at air temperature. When the wind is not blowing as much, we don't feel as cold. So the skin surface is not at. So type 3 boundary condition, then how do I write it? So first let's look at the schematic. So if this happens to be your cheek surface, so this is the tissue and this is the air, okay, and you're losing heat because outside is cold, then the temperature profile can look something like that, colder into the surface of your skin and then even colder as you get far away. So all we can say at this point is the however much heat coming in from the left is the amount that you are losing to the air. So the amount from the left is minus k del T del x at x equal to 0. That's the heat conducted into the surface, right? This is the conductive heat flux. So this is the heat. So heat conducted to the surface must be equal to the heat convected away using our convective heat transfer formula, H times temperature here minus T infinity. Temperature at x equal to 0 . So all this equation says, I want you to see the big picture, that, well, whatever is coming to the left should be equal to what's going to the right, because it's a line. There is nothing else that can happen. This doesn't have any mass, this line. So whatever comes from the left should be equal to what's going to the right. So how do I write this? a blowing wind, let's say at 10 degrees, and that has a heat transfer coefficient of 50 watts per meter square, I'm going to write it as minus k del T del x at x equal to 0 is equal to 50 the h value times t at x equal to 0 minus t infinity. Okay, so what is the big deal in all this? You notice that uh, depending on T infinity, if T infinity is colder, if the air is colder, then our temperature profile can change. So the surface temperature can change depending on T infinity. So the surface temperature is not given to us. What is given is the T infinity. So this is contrasting with type 1 where the surface temperature was given. Here the surface temperature is not. Surface temperature depends on the situation. Surface temperature depends on T infinity. For example, what is the boundary temperature? Surface temperature depends on what is the value of H. So this is different from type 1. Now in the special case of H being very large, type 3 boundary condition becomes same as type 1 boundary condition. Let's look at it now, and we're going to keep coming back to this at other times. So the type 3 boundary condition looks this way, right? This is what we just wrote, type 3 boundary condition. If I rewrite that, t at x equal to 0 minus t infinity is equal to minus k del t del x equal to 0 at x equal to 0 divided by h. So when h is large, when h goes to infinity, then this ratio goes to 0, right? So under those conditions, when h goes to infinity, then t at x equal to 0 is equal to t infinity because the difference is 0. What does this mean? This is not some fictitious imaginary thing. We know that in the winter, given the same air temperature, it feels colder if the wind is blowing harder. If the wind is blowing harder, which means H is increasing. If H increases, then your surface temperature gets closer to the air temperature, so it feels colder. This is just a statement of that, and we're going to come back to this many more times later on. So now is the time for 2 questions. For these questions in a live class, I give 2 minutes for you to think about, and then I ask you. So in this case, once you hear the question, you should pause the video, take 2 minutes trying to answer, and then look at the answer. Okay. So the first one is you're taking shower. So there's water hitting your back surface, and there is a continuous supply of, let's say, warm water. What is the boundary condition at the surface? So now you should pause the video and take the 2-minute pause to think about the answer. So here is the answer, or one of the possible answers. So if this is your back, and there is water flowing this way, you see, I do not know what is the back temperature. What I know is the warm water temperature and maybe the H value at the back, as depending on how the water is flowing. So the temperature profile here would look something like this. If you were cold, if this is colder, and then the hot water is the warmest, and until it cools down by your back, and then inside it's going to look something like that into your body temperature. So we do not know. We do not know. What we know has to be true is the heat supplied by water must be the heat going into your back. So minus K del T del X at x equal to 0 is what is going into your back. That must be equal to H at times T at x equal to 0 minus T infinity. Okay? So this is not known. But we have this extra condition, and that's the convective boundary condition. So this is an example of type 3 boundary condition. So here is the second example. So we have a hot pad that is heated and it's placed on the back. What should be the boundary condition over the body surface? Okay, again the answer now is, again we have the pad on one side and the skin on the other side. So here we get into a long discussion because there are a few possibilities. One, the simplest one is the pad for a short time, it just keeps it at a Ts equal to T pad. So this is my type 1 condition. Okay. But as we will see later on, this problem is actually more complicated because the pad cannot just keep maintaining this as it's losing heat. As the pad loses heat to the skin, the pad temperature must go down. So a very realistic condition would go something like this. So this is your pad, and this is the heating pad and the skin, and so what you say at this condition is whatever the heating pad is losing is the same amount that the skin is gaining. That, in other words, the condition is minus K del T del X from the left side, x equal to 0, left side is equal to minus K del T del X, x equal to 0 on the right hand side. We are not going to deal with this. This is automatically satisfied. Okay. And so the simplest boundary condition in this case is simply the surface of this is equal to the pad temperature. Okay. So the last discussion in terms of boundary condition is what's called the initial condition. It is sort of a boundary condition for time, but it is conventional to call it initial condition when a process is transient, meaning the temperatures are changing with time. How in the world would you know the final temperature if you didn't know what you started with? So you need the initial temperature that you started from. So in summary then, we have the governing equation that we derive. This one happens to be showing the Cartesian coordinate one. And what is the meaning of it? How did we get it? It combines conservation of energy with Fourier's law. So conservation of energy, second law, with Fourier's law, meaning the mode of heat conduction. So you choose the equation in the right coordinate system for the given geometry. So if it's a cylinder, you choose in cylindrical coordinate system. These terms, each one of these terms represent physical process. I want you to I want to remind you that we don't just think of these as a math equation. Every term has a physical meaning: conduction, flow, generation, and storage. So this one, for example, is the storage, and this one is flow, this one is conduction, and this one is generation. So terms may be dropped depending on the situation. That makes our life easier. We're not always going to solve this big equation. We're only going to solve small parts of it. And the bioheat equation that we did is only a special adaptation of this energy equation. Then we talked about boundary condition, and boundary conditions are conditions at the surface that needed to solve the governing equation for a specific situation. Otherwise, we get general answers. Find out we have to find out which one applies at the boundary. So there are three types of conditions that we said. One is temperature is given, other is heat flux given, and the third one is the convective heat transfer, which simply says conducted heat is equal to convected heat. So you choose exactly one on one boundary. You cannot use two boundary conditions on the same boundary. You need two for each spatial variable. So if you're doing this for a slab, it has two boundaries, so to say. So you need two conditions. If you're doing a 2D slab, then you have 1, 2, and then 3, 4. So 2 for each dimension. Initial condition is needed for time t equal. Finally, we'll just have a short and quick overview of the step-by-step solution to many heat and mass transfer problems that we will do in this class. So I want you to see the big picture of such solution process. You start from a physical situation, then you draw a schematic, and I'll come back to the details of this process. So once you have the schematic, then you choose the governing equation for the domain, and then you choose the boundary conditions. Then you think of how am I going to solve these. So the solution technique that we'll talk about in a second, solution to the problem really is intended to understand better the physical situation. Okay, so the solution is going to give a fresh, improved understanding. That's why we're going through all this. From the physical situation, we go through this step because we want to have an improved understanding. Okay, so now a little bit of the detailed steps. So the schematic, when you try to do schematic, you think of, okay, which region am I solving for? Are there symmetry? These are things that we'll spend a lot of time later on. So this is just an overview. Governing equation, you try to decide whether it's Cartesian, cylindrical, or spherical. Is it 1D, 2D, 3D? Then are the terms transient, transient term, the flow term, the conduction term, storage, are they all needed? So those are the decisions that you make for governing equation. Likewise, for boundary conditions, you decide how many do I need? Do I need the temperature, that's type 1, flux, that's type 2, or type 3 convection? Or is the problem transient, so we need an initial condition. Finally, we decide which way am I going to solve the equation. There are two general ways of solving, analytical and numerical. In this class, we're only going to do simple analytical solutions, and we will not do numerical solutions.